So we're going to review how to add counting and whole numbers. Let's say we want to add 26 apples to 59 apples. Then we would have to count 59 past 26. Do you want to do that? Do you think it's practical? I don't want to sit there and count 59 above 26, which would mean you would have to go 26, 27, 28, 29, 30, 31, 32, 33, and so on. I'm not sitting there counting 59 apples. So when mathematicians encounter a difficult problem like that, they resort to looking at the logic behind adding numbers. So you know how to add all numbers from 0 through 9, right? Because so the largest addition would be 1 plus 9 would be 10, 2 plus 9 is 11, and so on. 9 plus 9, so you don't have to count 9 above 9. So that would be 10, 11, 12, 13, 14, 15, 16, 17, 18. So 9 plus 9 is the largest addition that you would have to perform in numbers 0 through 9. Once you know how to do that, you can pretty much add any counting numbers and whole numbers. Well, how is that? Let's take a look. So you can think of 26 apples. Remember, we have decimal system, so you can think of it as 2 boxes of 10 apples and 6 loose apples, because 2 is in the tens place, 6 is in the units place. Whereas 59 apples would be 5 boxes of 10 apples and 9 loose apples. So here's our addition. You have number of boxes and number of loose items, or units place, tens place. 6 loose apples and 9 loose apples. This 9. So what we can do is take one of the apples from the 6 and add it here. That will give us another box. So the 9 will now become 1 box. And so now you have 5 apples left here, and you have 8 boxes. Can you see that? Let's go over it again. So 6 and 9 loose apples. One of the 6 apples we can put into the 9 apples and make 1 box out of it. And then we have only 5 loose apples left. So 5 loose apples, 5 loose apples, and then 8 boxes. And that is the process of adding counting numbers or whole numbers, and in fact any decimal numbers. So a standard algorithm to add any decimal number is to keep track of the units place, tens place, hundreds place, similarly tenths and hundredths. So how many more places there are? If there's some places are missing, you can put zeros in its place, but the way to add them is in boxes. So if you have 10 of them, then they move into the next place value. So for example, we start always from right to left, because the smaller ones, if there are more than 10, we can make another box and it will go up there. So take a look. So the standard algorithm for adding decimal numbers would be matching place values and then doing what we did with the apples there. So 6 and 6 will give me 12, but I can't have 12. This is a singleton spot. So 12 means I have 2 singletons and 1 box of 10. So 2 singletons and then the 1 box of 10 would have to, so in other words, 10 100ths make 1 group of tenths. So now you have this many tenths. So when you add them, you're going to get 10. You can't have 10 here, so there will be 0 singletons and 1 units place. And then when you add them, same thing. You just keep going like that. And we call these numbers carryovers. And so if there are carryovers, you just take them over into the column and add them together. If there was a carryover here, it would just go into the next digit there. Does everybody understand? If not, pause and rewind. So this is something you have done in K through 12 education, where you add the numbers by adding the place values, same place values. That's like having same units. You're adding the hundredths together, tenths together, units placed together, tens placed together, and hundreds placed together. And then having carryovers if you have to. And so here, if you had a carryover, you just go over. I ask you as a video log question now to think about what is the largest carryover number you're going to get. Is it possible to get a carryover number more than 1? Think about it and write that as your video log questions. So, what's the largest number you could get from adding 2 single-digit numbers? Can there be a carryover of more than 1? Explain why or why not for your video log questions. All right, so let's recall that the decimal number addition, another way to look at it would be, you can think of powers of tens as units of that place or hundreds as the units of that place, just like centimeters or apples. So in the expanded notation, when we write the two numbers, 321 and 507, the units, tens, hundreds, or 10 squares are the units that you're adding. And so in order to add these numbers together, remember what we did? We added the 7s and the 1s, 0 and the 2. So it would look like this. You're adding the units placed together, tens placed together, hundreds placed together. But in the expanded notation, it will look like this. Think about what arithmetic property, what addition property did we use to be able to do this process? Remember, we have associative property of addition and commutative property of addition, and both those are needed here in order to be able to add the 10 squares together and the tens together and the units placed together. And so this process is very important of adding similar units because we can then expand that process to polynomials. So here, 8 10 squares, 2 tens, and 8 singletons, the answer will be 828. But if you expand that process to polynomials, this is how it would look. You're doing the exact same thing. Look at the similarity between here and here. You have 3 plus 5 10 squares versus x squares. 2 plus 0 tens versus x's. 1 plus 7 10 to the 0 versus x to the 0, which is just 1 basically. And so the only difference between decimal addition and polynomial addition is that you don't have a carryover, and it's not going to be 828. It will be 8x squared plus 2x plus 8. The reason this addition symbol has to stay there and we can't just say 828 is because x squared is a different unit than an x, and x to the 0 power or singleton is a different unit than x. So we have three quantities here with different units, and that's why they have to stay as they are, as separate quantities with the addition sign in between. So look, this is very, very important how here we combine them together and a notation says 828. Whereas here the plus sign is going to be visible because you have different units and you can't really write them as one quantity. So the two polynomials added to give you another polynomial. And so we say that polynomials are going to be closed under addition. In other words, you add two polynomials and you get another polynomial. So decimal number addition is very much the same as what we're doing with polynomial addition. If you did your video log questions where we asked you to take two different objects and add them together, hopefully you saw the same observations. Let's see if you did complex number addition then. Suppose I gave you two complex numbers, did not tell you how to add them. Pause the video here and see if you can come up with a way to add them. Remember what we did with polynomials. You can treat I as a complex number, so imaginary number part. Remember, I was square root -1. So some of you told me that you can add two real parts together and two imaginary parts together to end up with this. So you're going to have 8 for real part and 11 for imaginary part. And you are absolutely correct. That is exactly what we're going to do. Add real parts together, imaginary parts together. It makes the most sense. So you should think about addition of two quantities as not somebody has to come and teach it to you, but if you just think about the process, adding like terms, then you'll have no problems adding any two mathematical objects that you've studied so far. So remember that square root -1 is what I was. So you can think of expanding, adding complex numbers to radical terms then. What if you ended up with these terms added together? because of commutative property and associative property of addition, we can combine like terms together. You can see square root 2 is like a unit then. So I can add 3 square root 2's and 4 square root 2's and 5 cube root 3's and 6 cube root 3's together to end up with 7 square root 2's and 11 cube root 3's. It's like square root 2 is like an apple or a centimeter, and cube root 3 is like orange or inches or something of that nature. So in other words, when you're adding radical terms, square root 2 and cube root 3 served as units. Let's try to see if you can add these. I'll pause for a few seconds, see if you can come up with a way to add these two objects. So you have this object and this object, there are 4 terms. What do? That's correct. You can add the a to the 2/3 and b to the 4/5 together. And so that will give you this. Again, a to the 2/3 acted as a unit. Then there are 3 of those and 5 of the same will give you 8 of the same. 7 of this and 3 of these will give you 10 of those. Now remember, we didn't do anything to the power 2/3 is because that was a unit. The power did not change because a to the 2/3 was acting like an apple. Does that make sense? So we're adding, look at all the similarity between these additions and polynomial additions. You can only add like terms if they look similar to each other. You have whole number part here or decimal number part here, but then a quantity here that you cannot do anything with, same thing here, then those two are similar looking objects. And so same unit objects, I should say, not similar looking, same unit objects, and then you can add them together. So adding radical expressions practice questions. See if you can do these. Oops, sorry. All right, so the first one I'll do for you. So you can see square root 2's are added together and cube roots are added together and you end up with that. We saw that before. Now do the other ones on your own. All right, so these 2 examples that are done here is what we saw in the previous slide. And so now see if you can expand that to this. Which 2 are going to be similar units, do you think? Is square root x and square root x plus 1 the same? Well, no, because this is x plus 1. The radical has x plus 1 inside here versus here's the radicand is x. So you only can add 2 radicands that are the same together. So you have 3 of those and 6 of those and 5 of these and 7 of those, and then that will be your answer then. So 9 square root x's and 12 square root x plus 1's.